Our goal with the next couple of videos is to come up with some anti-differentiation rules, sort of like we did for the derivative rules. We're just working that process backwards. So our first function here is f of x is equal to k. K is some sort of constant. If I were to take the derivative, what's the derivative of a constant? Like, for example, this is f of x is equal to 3. You take its derivative, that's just going to be 0. So f prime of x is equal to 0. Now what I want to do is take this is my derivative equation, my differential equation. I want to work it backwards to find the original function that it came from. I want to know what is its antiderivative. So the antiderivative of 0 is going to be some sort of constant. The problem is I don't know what that constant was. This was the number 3, but when I took its derivative, I lost the identity of that constant. So the best that I can hope for is some constant that I'm just going to call c. That constant and this constant may not be the same thing. Okay, let's say that I have, this is the a linear function here, basically. F of x is equal to k times x. K is some sort of, it's like the slope that's in front of this. Maybe it's 2x. I take its derivative and I just get 2. In this case, it's f prime of x is equal to k. So if I have my differential equation equal to some constant whenever I want to work it backwards, it's going to turn into a linear equation. It's going to be kx. But this could have had some sort of constant that is added to the end of this, and I lost it when I took the derivative. So I have to make sure I hit plus c at the end of it. Okay, next up is the constant multiple rule. So if I have a constant multiplied times a function, when I take the derivative, that constant just comes along for the ride. So f prime of x is going to be equal to k times g prime of x. So let's say I wanted to work this problem backwards to find its antiderivative. This k is also going to come along for the ride. So this k is going to come into the antiderivative, but we're going to multiply it times the antiderivative of this g of x function, which I'll just denote as a capital G. However, there could have been some sort of function or some sort of constant that was added to the end of this, which I lost, so I'll have to make sure I put a plus c at the end of it. Next up, we have the sum rule. So the sum rule and the difference rule would work exactly the same way. I want to take the derivative of the sum of two functions, and it is the sum of the derivatives of those two functions. So f prime of x is equal to g prime plus h prime. If I wanted to work backwards from this, here's my differential equation. Works exactly the same way. I would just have to make sure that I added a plus c at the end. So the antiderivative of the first function plus the antiderivative of the second function, and then add a c because there could have been a constant that I lost when I took the derivative. All right, remember that e to the x, that exponential function, super special because when you take its derivative, it's the exact same function that you started with. It's still e to the x. So when I take its antiderivative, take the antiderivative of this, it's also going to be e to the x, but it could have had a plus 1 or a plus 17 at the end of this thing. And I don't know that, so I'm going to have to add a plus c at the end of it. Let's look at a couple more of these things. So here I have just a general exponential function. The base is b, not necessarily an e. So I know that when I take its derivative, remember I had to scale it. I had to scale it by the natural log of that base. So its derivative is the natural log of b times b to the x. So if this is what you have as your differential equation, when we work that process backwards, we know that the antiderivative should be b to the x, and then don't forget your plus c. The problem with that is that you don't usually see it like that. You're not going to see it with this natural log of b being multiplied times the front by that b to the x. Usually you're just going to see it as b to the x, and it's going to be missing this thing. Okay, so that means that the original function must have been b to the x divided by the natural log of b. So the antiderivative of this is b to the x divided by the natural log of c, natural log of b, yes, plus c. Let me explain why that happens, right? So let me come over here so I can write a little bit. And I'm going to say that this is based on the derivative rule for exponential functions, if this is my function, b to the x, I know that its derivative is supposed to be natural log of b multiplied times b to the x. Okay, so our goal here is to be able to work this thing backwards. But this is what I have. I only have b to the x. So I'm going to just say that, hey, this is my function here that I was given. It's b to the x. I want to work it backwards. But I need to use a differentiation rule on it. And I'm missing this thing, this constant that we had to scale it by because its base was not e. So I'm going to force it in there. Let me just move this over a little bit. And I'm going to force in this natural log of b so that I can use the differentiation rule. But I just changed the value of this thing. So since I changed the value of it, I need to change it back. And the way that I change it back is by dividing it by the natural log of b. So basically what I just did is I multiplied this thing by a fancy 1, because the natural log of b divided by natural log of b, that's just 1. And now when I take a look at just the top part of this thing, I can apply this derivative rule right here, and I know that the antiderivative of natural log b times b to the x must be just b to the x, which leads us to the antiderivative rule of b to the x over the natural log of b. And don't forget your constant integration. So here's one way to think of this. Taking the derivative and taking the antiderivative are inverse operations of each other. Because they undo each other in this kind of way. Like, for example, if I add 7, I subtract 7 so I can go back to where I originally was. Those are inverse operations, adding and subtracting, multiplying and dividing, squaring and taking the square root. So taking the derivative and taking the antiderivative are inverse operations. So think of it like that. When I take the derivative of b to the x, I'm going to multiply it by the natural log of b. When I take the antiderivative, instead of multiplying by the natural log of b, I'm going to divide by the natural log of b. Again, think of it as inverse operations. Here you got to multiply, and there you have to divide.